Transformer calculations involve several key formulas. Firstly, the transformer kilovolt-ampere rating is calculated by dividing the power in kilowatts by the product of the voltage in volts and the power factor. Secondly, transformer secondary current is found by multiplying the output power in kilovolt-amperes by 1000 and dividing by the product of the voltage in volts and the power factor. Thirdly, transformer primary current is calculated by dividing the secondary current by the transformer ratio. Fourthly, transformer impedance in ohms is calculated by squaring the voltage in volts and dividing by the power in kilowatts. Fifthly, transformer regulation is determined by subtracting the full load voltage from the no-load voltage, dividing the result by the no-load voltage, and then multiplying by 100%. Moving on to commercial service calculations, the total connected load is the sum of the connected loads of all equipment. The demand factor is the ratio of the maximum demand to the total connected load. Service ampacity is calculated by dividing the total connected load in kilowatts by the product of the voltage in volts, the power factor, and the demand factor. Service voltage drop is calculated by multiplying the distance in feet by the load current in amps and the resistance in ohms per foot. Service impedance is the sum of the resistance in ohms and the reactance in ohms. For transformer kilovolt-ampere rating, it's crucial to accurately determine the power factor, as it significantly impacts the final kilovolt-ampere value. The power factor represents the efficiency of the electrical system, with a lower power factor indicating a less efficient system and a higher kilovolt-ampere requirement for the transformer. Regarding transformer secondary current, understanding the load characteristics is essential. Different types of loads, such as resistive, inductive, or capacitive, will affect the power factor and, consequently, the secondary current. For transformer primary current, the transformer ratio is a critical parameter. It represents the relationship between the number of turns in the primary and secondary windings and directly affects the current transformation. When calculating transformer impedance, it's important to consider both the resistance and reactance components. Resistance is the opposition to current flow due to the material's properties, while reactance is the opposition to current flow due to inductance or capacitance. For transformer regulation, a low regulation percentage is generally desirable, as it indicates a more stable voltage output under varying load conditions. This is crucial for sensitive equipment that requires a consistent voltage supply. When determining the total connected load for commercial service calculations, it's important to consider all electrical equipment, including lighting, HVAC systems, appliances, and any other devices that draw power. The demand factor is a crucial element in commercial service calculations, as it accounts for the fact that not all connected loads will operate simultaneously at their maximum rating. This factor allows for a more accurate determination of the required service capacity. Service ampacity calculations must adhere to local electrical codes and regulations. These codes specify the minimum ampacity requirements based on the connected load and other factors. Service voltage drop can significantly impact the performance of electrical equipment. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The service impedance plays a crucial role in determining the voltage drop and fault current levels in the electrical system. Lower impedance generally results in low voltage drop and high fault current. Furthermore, consider the impact of harmonics on transformer and service calculations. Harmonics are distortions in the voltage and current waveforms that can increase losses and stress on electrical equipment. When calculating transformer size, ensure to account for any future load growth. Oversizing the transformer slightly can provide additional capacity for future expansion and prevent overloading. Regularly inspect and maintain transformers to ensure their optimal performance and longevity. This includes checking for signs of overheating, corrosion, and loose connections. For commercial service calculations, consider implementing energy-efficient measures to reduce the overall connected load and demand. This can include using energy-efficient lighting, HVAC systems, and appliances. Regularly monitor the electrical system's performance to identify any potential problems or inefficiencies. This can involve using power quality meters to measure voltage, current, power factor, and harmonics. Ensure that all electrical work is performed by qualified and licensed electricians to ensure safety and compliance with local codes. Proper grounding is essential for both transformer and commercial service installations to prevent electrical shock hazards and ensure proper equipment operation. Consider the use of surge protection devices to protect sensitive equipment from voltage surges caused by lightning or other events. Regularly review and update electrical system calculations to account for any changes in load or equipment. When selecting transformers, consider the ambient temperature and altitude, as these factors can affect the transformer's rating and performance. Ensure that transformers are properly ventilated to prevent overheating and maintain their optimal operating temperature. For commercial service installations, consider the use of a backup power system, such as a generator or an interruptible power supply, to ensure continued operation during power outages. When designing electrical systems, consider the impact of electromagnetic interference and take steps to mitigate its effects. Ensure that all electrical equipment is properly labeled and identified to facilitate maintenance and troubleshooting. Regularly train personnel on electrical safety procedures to prevent accidents and injuries. Follow all applicable safety regulations and guidelines when working with electrical equipment. In addition, understanding the transformer nameplate data is critical. The nameplate provides essential information about the transformer's specifications, including its kilovolt ampere rating, voltage, frequency, impedance, and insulation class. The impedance value is crucial for calculating fault currents. A lower impedance transformer will result in higher fault currents, which requires careful coordination of protective devices like circuit breakers and fuses. The insulation class indicates the maximum operating temperature of the transformer's insulation. Exceeding this temperature can lead to premature insulation failure and transformer damage. The frequency rating indicates the frequency at which the transformer is designed to operate, typically 50 or 60 Hz. Operating the transformer at a different frequency can affect its performance and lifespan. The voltage rating specifies the primary and secondary voltages of the transformer. It's essential to ensure that the connected equipment is compatible with these voltages. The kilovolt ampere rating indicates the transformer's maximum apparent power output. It's important to select a transformer with a kilovolt ampere rating that is sufficient to handle the connected load. The transformer's vector group describes the phase relationship between the primary and secondary windings. This is crucial for paralleling transformers and ensuring proper system operation. Furthermore, when performing commercial service calculations, consider the diversity factor, which is similar to the demand factor but accounts for the diversity in the types of loads connected to the service. Also take into account any nonlinear loads such as electronic ballasts and variable frequency drives that can generate harmonics. Harmonics can cause overheating of transformers and other electrical equipment and can also interfere with the operation of sensitive electronic devices. To mitigate harmonics, consider using harmonic filters or specifying harmonic-resistant transformers. The NEC, or National Electrical Code, provides guidelines for sizing transformers and service conductors based on the connected load and other factors. The NEC also specifies requirements for grounding, overcurrent protection, and other safety aspects of electrical installations. The ambient temperature can also affect the ampacity of service conductors. Higher ambient temperatures can reduce the ampacity of conductors, requiring larger conductors to be used. Also consider the voltage drop in the service conductors. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC specifies maximum voltage drop limits for both feeders and branch circuits. The short circuit current rating of the service equipment must be sufficient to withstand the available fault current at the service entrance. Furthermore, the grounding system is crucial for safety and proper operation of the electrical system. The grounding system provides a low impedance path for fault currents to flow back to the source, allowing overcurrent protective devices to operate and clear the fault. Grounding electrodes, such as ground rods and ground plates, are used to connect the grounding system to the earth. The size and type of grounding electrode required depends on the size of the service and the soil conditions. The grounding electrode conductor connects the grounding electrode to the service equipment. The size of the grounding electrode conductor is based on the size of the service entrance conductors. The equipment grounding conductor provides a path for fault currents to flow back to the source from electrical equipment. The size of the equipment grounding conductor is based on the size of the circuit conductors. Bonding is the process of connecting all metallic parts of the electrical system together to create a low impedance path for fault current. Bonding helps to prevent voltage differences between metallic parts, which can be a shock hazard. Surge protection devices protect electrical equipment from voltage surges caused by lightning or other events. Surge protection devices divert the surge current to ground, protecting the equipment from damage. Consider the use of uninterruptible power supplies for critical loads such as computers and medical equipment. UPS systems provide backup power in the event of a power outage, ensuring continued operation of the equipment. Regular maintenance of electrical equipment is essential for ensuring its safe and reliable operation. Maintenance activities include inspecting equipment for damage, cleaning equipment, tightening connections, and testing protective devices. Also, power quality monitoring can help to identify and diagnose electrical problems. Power quality meters can measure voltage, current, power factor, harmonics, and other electrical parameters. The data from power quality meters can be used to identify and correct problems such as voltage sags, voltage swells, and harmonic distortion. Another important element is the application of appropriate safety procedures when working with electrical equipment. These procedures include energizing equipment before working on it, using personal protective equipment, and following lockout/tagout procedures. Electrical safety training is essential for all personnel who work with electrical equipment. Training should cover topics such as electrical hazards, safety procedures, and the use of personal protective equipment. Moreover, the selection of appropriate electrical equipment is crucial for ensuring the safety and reliability of the electrical system. Equipment should be selected based on the connected load, the operating environment, and the applicable codes and standards. The installation of electrical equipment should be performed by qualified and licensed electricians. Installation should be performed in accordance with the applicable codes and standards and the manufacturer's instructions. The documentation of the electrical system is important for facilitating maintenance and troubleshooting. Documentation should include drawings, wiring diagrams, equipment specifications, and maintenance records. Energy efficiency is an important consideration when designing and operating electrical systems. Energy-efficient equipment and practices can help to reduce energy consumption and save money. Moreover, consider the impact of the electrical system on the environment. Sustainable practices can help to reduce the environmental impact of the electrical system. Recycling electrical equipment is an important way to reduce waste and conserve resources. The design and operation of electrical systems should be based on sound engineering principles. Engineering analysis can help to ensure that the system is safe, reliable, and efficient. Continuous improvement is essential for ensuring the long-term performance of the electrical system. Regular review and improvement of the system can help to identify and correct problems and optimize performance. These comprehensive transformer and commercial service calculations, combined with the additional considerations for safety, maintenance, and energy efficiency, are vital for the reliable and effective operation of electrical systems. Firstly, understanding transformer voltage regulation is key. It describes the change in secondary voltage from no load to full load conditions. A lower regulation percentage means a more stable secondary voltage under varying loads. Secondly, consider transformer inrush current, the high peak current drawn when a transformer is initially energized. This inrush current can be several times higher than the normal operating current and needs to be considered when selecting overcurrent protection devices. Thirdly, transformer cooling methods vary. They include air-cooled, oil-cooled, and forced air-cooled. The appropriate cooling method depends on the transformer size and operating environment. Fourthly, insulation resistance testing is a crucial maintenance procedure. It measures the resistance of the transformer's insulation to ground and can identify potential insulation failures. Fifthly, turns ratio testing verifies the accuracy of the transformer's turns ratio, which is essential for proper voltage transformation. Sixthly, dissolved gas analysis is used to detect and analyze gases dissolved in the transformer oil. These gases can indicate various types of transformer faults, such as overheating or arcing. Seventhly, partial discharge testing detects small electrical discharges within the transformer insulation. These discharges can be a sign of insulation degradation and can lead to eventual failure. Eighthly, consider power factor correction. Improving the power factor of a commercial facility can reduce energy costs and improve the efficiency of the electrical system. Ninthly, harmonic mitigation techniques include using harmonic filters or specifying harmonic resistant transformers. These techniques can reduce the negative effects of harmonics on electrical equipment in the power system. Tenthly, energy audits can identify opportunities to reduce energy consumption in a commercial facility. These audits can help to save money and reduce the facility's environmental impact. Finally, preventative maintenance programs are essential for ensuring the long-term reliability and safety of electrical equipment. These programs should include regular inspections, testing, and cleaning of equipment. Also, consider the location of the transformer. The transformer should be installed in a well-ventilated area to prevent overheating. If the transformer is installed outdoors, it should be protected from the weather. Furthermore, consider the noise level of the transformer. Some transformers can be quite noisy, so it is important to choose a transformer that is appropriate for the environment. Transformers can generate heat, so it is important to consider the heat load when designing the electrical system. Also, consider the weight of the transformer. Transformers can be very heavy, so it is important to ensure that the building structure can support the weight. The NEC Article 450 covers transformers. It covers transformer overcurrent protection and transformer location and more. Furthermore, NEC Article 220 covers branch circuit, feeder, and service calculations.